It's really sort of a random chance what body collides with what other body to yield the final planets. One of these chance collisions happened to occur at just the right angle with just the right speed to form our moon. And when you view it in that way, the fact that Earth ended up at such a habitable distance from our sun with our large moon seems to be a very fortuitous event. The specific type of impact needed to form a moon as large as our moon is actually fairly unique.
Had Orpheus hit head-on, Earth wouldn't have a moon. The angle of impact would throw up a ring of debris, but because it was within the Roche radius, the debris would rain back to Earth.
Yet in other cases, we find that after an impact, perhaps we form two moons that are actually stable for tens of thousands of years.
Canup tries every angle in her Orpheus impact models. A third of her simulations yield two small moons, but they're unsustainable partnerships. Alas, two moons wouldn't last till today.
What a sight that would have been to have two moons in the sky, in very close to the Earth.
With two moons, the smaller inner moon either falls to Earth, or the moons ultimately collide. But to produce our moon, Canup takes the most oblique approach.
We found that if you made the impact occur at a very off-center angle, so that the impactor almost missed the proto-Earth entirely, that configuration was very good at placing material into orbit. An off-center impact partially destroys the impacting body, which then passes away from the Earth and temporarily recoalesces before coming back in again for a second hit.
A double whammy.
The entire impact process probably took on the order of a couple days, but it would have been a very bad weekend to be on the Earth.
But our prize is the moon. It forms just outside the Roche radius, 14,000 miles from the surface of Earth Mark II. Accumulating ejecta from a hot disk of debris, our moon rapidly coalesces in from just 1 to 100 years.
If we had been on the Earth right as the moon formed, say 100 years after the impact, the moon would have been truly an enormous sight in the night sky. When you viewed the moon right after it formed, it would have appeared 15 times as large in the night sky as it does today. That would have been quite a sight.
Scientists know by examining rock layers called tidal rhythmites. They show the frequency of prehistoric tides. Marjorie Chan of the University of Utah hunts rhythmites in Big Cottonwood Canyon. Eons ago, these were layers of sediment left by tides in a river estuary.
Some of these tidal rock layers are just paper thin, and it's like each piece of paper is a story or page out of a diary telling what's happened a billion years ago.
Chan's findings are rock solid. Primitive tides are more frequent, and the days far shorter.
It's amazing that these tidal rhythmites can tell us that a day was only 18 hours long, because we can count some of the tidal rhythms. We can see how many rhythms were in a day, how many days were in a month, how many months were in a year. And we use those calculations to show how the moon has been moving away from the Earth over time.
From 14,000 miles at the start, the moon is now 234,000 miles from Earth. Today, when all three bodies align, the moon can precisely cover the sun. On Earth, we see it as a total eclipse, an astonishing cosmic coincidence. Such eclipses are further evidence that the moon is receding from Earth. This is a total eclipse today, but it looked like this when the moon was closer to Earth. In future, when the moon is further away, a total eclipse will be a thing of the past. Ancient eclipse records reveal that as little as 2,000 years ago, day length is fractionally shorter than today. Had it been constant, the solar eclipse of 136 BC would have followed this line of totality. Instead, because the day was then shorter by a 20th of a second, totality sweeps east through Babylon. More than a quarter century ago, Apollo astronauts set up reflectors on the moon. Today, they're targets for astronomers at the McDonnell Observatory, Texas. By bouncing laser beams off the reflectors, the speed at which the moon is receding can be measured to within a hair's breadth. The gap is widening by 1.5 inches a year. From this, over 4.5 billion years, the moon in our skies has shrunk to this. The moon's gravitational pull keeps Earth on an even keel, an average tilt of 23 degrees. By contrast, Mars lacks a big moon stabilizer. Consequently, it wobbles on its axis. Over millions of years, the tilt can vary from 0 to 90 degrees, playing havoc with its climate. Imagine Earth like this. In Paris, at the Bureau de Longitude, astronomer Jacques Lascar does just that. What would happen to Earth, he wonders, without our big, lucky moon? First, he models Earth with the moon. Our axis may move in a circle, but always at 23 degrees. Remove the moon, and the circular movement slows, but Earth goes loco. Lascar's calculations spell chaos. Take out the moon, and we lose all stability. Earth reels around the inner solar system. Lascar has no doubt we depend utterly on our partner in space.
If we had no moon, the axis of the Earth will wobble chaotically between 0 degree and 90 degree. And the climate on the Earth would change dramatically. So we can say that the moon is a climate regulator for the Earth.
Even with the moon, Earth suffers many wobbles. As a member of a NASA team seeking the origins of life, Lynn Rothschild knows that even the smallest change in tilt has profound effects.
There's some researchers in Germany that have proposed that the reason that civilization on Earth started in the Nile Delta region and not the Sahara, where there were large groups of humans at the time, was because of the obliquity of the Earth shifting less than a degree.
North Africa's lush Sahara turns brown and barren. Today, it's Earth's biggest desert, product of a planetary teeter.
Without the moon, we would be getting shifts in obliquity of 20, 30 degrees, 40 degrees, 50, more. And so compare that to this change in obliquity of less than 1 degree that caused the mass migration of humans, and you can start to imagine what a serious issue this would be for life on Earth.
So, as we lose the moon, there's cause for concern. Could this be Egypt as Earth starts to wobble? Is this the Sahara of the future? Does Antarctica become a blazing desert? These are the prospects if we lose the moon and Earth tips over.
You suddenly have summers that are incredibly hot. Over land, you're talking about maybe over 100 degrees centigrade, over the boiling temperature of water. On the other hand, you have winters where you're well below freezing, maybe as cold as even dry ice, incredibly cold temperatures.
Ice sheets advance and retreat across the equator. Worse still, as Earth wobbles chaotically, the polar caps melt, the oceans flood, islands disappear, our coastal cities are inundated. It's a fact. The moon is leaving us. The further it goes, the less it will stabilize our planet, and the slower Earth will rotate. Our day will get longer and longer.